Okay, so in this video we're going to talk a little bit about a tool that we're going to use called a free body diagram. So going back to the momentum principle and thinking about how the net force gives you information about how the momentum of a system will change with time, we can use this information to figure out how a system is going to move. But what we have to do is first understand that that net force is made out of, or constructed out of, several forces or several interactions that a system might have. And so the free body diagram is a way of representing those forces in a picture to make sense of how the momentum will change. So let's take the example of a book that's sitting on a table. So here's your physics book, which we don't have in this class, but fair enough. And what you can tell me right now is that if the book is sitting here on the table, its momentum is not changing, right? We know that the book is at rest. So therefore, the net force that acts on that book better be zero. But let's think about the types of interactions the book has. The book interacts with the table, and the book interacts with the earth. And so if we were to draw a free body diagram, what we would do is we would take the book, we would crush it down to a point, and we would draw those two forces, or those two interactions. So we know that the gravitational force will pull down on the book, so the book experiences its weight force in the downward direction. And there's a force due to the table which points upward, and it must be that that force due to the table is precisely the same magnitude as the weight force due to the interaction with the earth. One thing that I like to do often is to write down that the change in momentum of this system is zero and that the net force is zero. This thing that we've written right here is a free body diagram. It's representing the system consisting of the book and how it interacts with the earth and the table in a diagram. We've crushed the book down to a point. We've allowed the two interactions, the two forces, to be drawn onto this diagram to illustrate that the weight force and the force due to the table are exactly the same size, but they point in different directions. We've also further indicated how the momentum of this book would change. So this is a really complete free body diagram. It's a really simple one in the sense that the momentum is not changing and the book is at rest. So it's easy to reason about. Maybe a more challenging one is to think about pulling a ball, let's say. So you have a ball attached to a wire, and you're pulling it upward so that the momentum is actually changing in that direction. That is, the ball is accelerating upward. Its speed is increasing in this upward direction. Okay? So we know that the momentum change is non-zero. In fact, we know what its direction is going to be. So because we know that the direction of the momentum change is upward, that net force that acts on the ball must also be upward based on the momentum principle. So we can draw the free body diagram for this. So what we have are two interactions again. We have the interaction with the earth, so there's a force that pulls down on the ball, the weight force. But we also have the interaction with the wire, the force that the wire exerts on the ball. Now it turns out, because we know that the momentum change points upward, and thus the net force also points upward, that weight, or that force due to the wire itself must be larger in magnitude than the weight force. They point in opposite directions, but the resulting net force points upward to indicate that the momentum, or the velocity, is increasing in the upward direction. So again, here's another free body diagram, which we'll often abbreviate as FBD, and it helps us to reason about how the two forces, the two interactions on the ball, give rise to the net force. Now, on the homework and so forth, you're going to deal with slightly more complicated situations where you'll have two-dimensional interactions and so forth. So, for example, you might have a situation where you have a block that is on a plane, and you'll have to deal with those interactions that are associated with the block on the plane. For example, if there's no friction here, there's an interaction with the block pushing perpendicular to the surface. There is an interaction due to the weight, which points down. And depending on what the block is doing, whether it's accelerating upward or downward or so forth, you'll have a relative difference in the strength of these two forces. I'll leave that as something that you'll work on your homework as well as in class.